Good morning. Sorry for the delay, but my name is Shahar Belkin, and I represent ZutaCore. I'm the Executive Vice President for Product at ZutaCore. And I want to talk about the white paper that we published with the Modular Data Center. That the link is right here for a modular data center that is based on direct-on-chip liquid cooling, or more than that, two-phase direct-on-chip liquid cooling. And dive in just a little bit about the ZutaCore involvement. In the last 2 years, we've been involved with OCP. We had helped the cold plate team to put in what means a two-phase cold plate and dielectric wetted material systems. We worked with the door heat exchangers in 2 ways of implementing a door heat exchanger and direct-on-chip liquid cooling, and in air-assisted liquid cooling as in the door. And we also worked with the heat reuse team. And the one thing about this white paper, this was a good project to implement all of them together with the modular data center in order to show the industry and to enable others to learn how to implement a system. And the modular data center gave us an advantage of having a full data center cooled by the two-phase direct-on-chip liquid cooling, or what I'm going to show is a hybrid solution of air and direct-on-chip liquid cooling. The challenge that we wanted to solve here is how to cope with a very, very high growing TDP of the CPUs and GPUs in the market that we all know, the fast growing of the high power racks and data centers, with the need for sustainability, for reducing the cost, reducing the power, and also adding the heat reuse to this combination, enabling a real sustainable data center and showing the capability by having a modular or a model that could be duplicated as a modular data center or as a building block in a big data center. And what we showed here that we can actually pack in a OCP data center, a 1 megawatt data center based on CPUs. Next stage will be the GPUs and the AI stuff. But what we did here is used 16 racks with rear doors, as you can see on the right of the screen, in a block data center, just like the OCP is using everywhere. The essence of this solution is hybrid cooling, meaning 70% of the high power chips, the chips with a high TDP and the high heat flux, are being cooled using the direct-on-chip liquid cooling. All other components are being cooled by air. That's about 30% of the heat is being cooled by air. And the combination of rack with the rear door shows that it's actually neutral to the temperature of the air in the room, in the modular data center. So it enters the rack at 35, exits at 35. 35 could seem to be a high temperature to a standard data center, but this is what we wanted to show, that you can use the 35 air temperature coming in, and the rack and the servers all work perfectly in that temperature, showing that you can use actually cooling water around 30, 35 degrees and reduce cost of cooling tremendously this way. Just explaining a little bit of why two-phase and why two-phase makes it different, I took this simple example that you can see on the left top corner, because when you're using latent heat, and all of us know that, when you have a pot of water and you put fire underneath, and I'm using fire because I don't want to use wattage, I don't want to use CPU, GPU, you're putting fire, it doesn't matter how strong the fire will be, the water in this pot will always be 100 degrees Celsius at atmospheric pressure, meaning that even if you put 2,000, 5,000 watt under a two-phase cooling pot, the water will never go over 100 degrees. And the reason I'm saying that is this water is what cools the surface of the pot and keeps it from burning, keeps it from heating up. It will never be above the 100 degrees that the water is there. That's the uniqueness of two-phase cooling. And the way that ZutaCore has implemented that two-way is exactly very similar, at least. It's called pool boiling, and structure that you see here of fins and wick is providing a solution that is creating a very, very efficient boiling without any bubbles on the surface, without any hot spots. So there is a wick material that is like a sponge material between the fins inside the cold plate that weak material is saturated by the liquid that is being boiled, and the boiling happens between that saturated liquid and the fins, creating a very, very efficient boiling, very small bubbles, and preventing the bubbles on the surface. That was the problem with evaporators, that they're not, that's the reason why they're not used to cool other chips, and that's what ZutaCore actually succeeded to create, and that is efficient boiling in an evaporator. Another thing is when you're trying to scale it up, you need to make sure that liquid comes to all these chips. So another mechanism built into those cold plates is what you see here is when boiling starts, evaporator starts, we lose liquid, the level of the liquid in the pool drops, and there's an orifice that opens up, more liquid comes in, and fully automated, on-demand solution that provides the amount of liquid needed all the time, so boiling and that cooling will happen all the time. The system is very similar to what we have discussed and what the cooling loop team here discussed in the OCP, and you have a link to the new document that was presented by them. What you can see is very simply cold plates inside the server connected to a manifold on the side of the rack that looks like exactly like the power distribution unit stuck on the side. All tubes, every server is connected by 2 tubes to that manifold, and the manifold connected on the bottom of the rack to a CDU or HRU heat rejection unit that removes the heat from the vapor, turning it back to liquid and pumping it back into the manifold into the server. Very simple loop, and just as it looks like. When you go back to that modular data center that we showed in the beginning, what we have is 16 racks, 63 kilowatt in each rack. Those are CPU racks that use the C series from Dell, so it's a HPC kind of configuration. In that data center, in that model, we have 2,304 CPUs of 350 watt, the SPRs. And what we can see that total power, we see that 806 kilowatt are being removed with the direct-on-chip liquid cooling, and another almost 200 kilowatt removed by air. When we have evaluated this solution in a location like Denmark, because of the weather, we see that we can get to a POE of 1.07 in this 1 megawatt data center. And if we're evaluating what is the heat reuse, we see that we can reuse 95% of the heat at 70-degree water. And this is a very efficient way of reusing the heat, because you already have 70 degrees, you do not need to reheat them or anything else. You can provide them directly to building heating. So think of a 1 megawatt data center in every neighborhood for heating up the buildings. So in this example, we see that a 1 megawatt data center is cooled by water. So you're cooling water outside, streaming the water in. And we show another example of a data center that is actually air-assisted cooling, meaning there is no water in this facility at all. This is air coming into the data center, cooling the servers, cooling the by direct-on-chip liquid cooling, air-assisted, and moving out from the data center, as you can see here. So air can come up all the way to 36 degrees in this case, and move out of the data center, of the modular data center, at 45 degrees. And the reason it's only 350 kilowatt is because that's the ability of air to cool it, because we couldn't get air lower than 36, it wouldn't make sense. And then when we're using the direct-on-chip liquid cooling air assistance, we see that we get actually to POE of 1.06. And we see that this kind of solution is not only efficient in energy, it's very efficient in cost. This is a very low-cost solution for a 350 kilowatt data center that has minimum facility for cooling. You see only the air-assisted and the direct-on-chip liquid cooling. No other facility is needed here. And so it's a cost-effective, it's a completely waterless solution. It's important for some of the market. And it's suitable for like telco, and as I said, in neighborhood. There is no real way of reusing the heat here, because the heat is moving out as hot air from the data center. So where do we want to go with this, and what's the next stage? From our point of view, there's two next stages to this white paper. One, as Carl said before, moving to a spec. So somebody can actually take it and manufacture this kind of modular data center. So moving with the OCP to a spec, but also moving a little bit higher into an AI modular data center, because today the AI is a big player in this market, and we see that we can get to this was a 80 kilowatt, we can go to 120 kilowatt racks with the new GB200 coming out very soon. So that will be the next spec. We'll have the next white paper. We'll have the AI GPUs in it. What we want to have is more people take advantage of this white paper, because this is actually a stepping stone to designing a data center that is using direct-on-chip liquid cooling, air-assisted or with water. And we will be very happy if people would join the modular data center, and because this is a very nice way of designing small cubes of data centers and then multiplying it in large data centers, because it helps you think about it, and a small way of everybody can actually cope the whole grasp of it, and the whole solution is one. Thank you. Any questions? Well, the design we have now for the GB200, we're looking at a 46U rack that comes to 120 kilowatt per rack. Well, by the way, it's about 3,000 watt per U. Just to.
Can you disclose the temperatures at which those GPUs are cooled? Can you go to your 7 degrees?
No, that's a very good point. The temperature there of at least the boiling temperature will be around 40 degrees Celsius. So the heat reuse will become a problem. The GPU is actually affecting negatively the sustainability of the data centers. Thank you very much.